So in case you didn't hear any things I said, I'm looking for the acceleration of this system. There's no friction on the table, no friction in the bearing with the pulley. The pulley is a regular disc, radius 15 centimeters, mass 50 grams. The mass on the table is 50 grams, mass at tongue is 25 grams. But you could do that in terms of M, with one of them being M and the others being 2M. Again, I want the acceleration of the system. So I'm just going to put the answer here because some of you are getting pretty close. That's really enough time. There's not much to this problem compared with yesterday. It's about the same as yesterday's question. So if you're struggling, you should have looked at your notes from yesterday. Let's start with the relatively straightforward stuff, shall we? How about we start with the one on the table? That box is experiencing a single important force. I know it's experiencing more than that, but the only one that matters is the tension to the right, which I'm going to label T1. Is that okay? And T1 is the only thing that's causing it to accelerate, so T1 equals 2ma. Net force equals ma. Any other questions? I'm going to make this direction positive, and therefore this direction of rotation is also going to be positive. The box that's hanging, it's experiencing two forces. An upward force of tension, which there's no reason to believe it's the same. In fact, I'm pretty sure it's different, so I'm going to call that T2. And a downward force of weight, which I'm going to label mg. Any question about that? All right. Mg minus T2 equals ma. Pretty straightforward so far. Now the pulley is experiencing a number of forces, probably like 4 of them. I'm expecting as it's experiencing a Newton's third law tension in this direction. It's experiencing a Newton's third law tension in this direction. I bet it's experiencing a force kind of in this direction for the mount. I don't know what you want to call that. Normal force is fine. I don't care. And it's probably also experiencing 2mg. Right, it's got weight. No reason to believe it doesn't. We didn't talk about that before, but it would. So I think those are the 4 forces acting on the pulley. But I think it's pretty clear the pulley is fixed in space and has a clear pivot point about its center. So if that's our pivot point, only 2 of these forces are causing torques. Now, I'm going to do this because I saw several of you doing it, but this is probably the last time. There are 2 torques acting in the system, torque 1 and torque 2. I'll write a little chart here, but I'm unlikely to write this chart anymore after this. All right? So let's start with tension 1 and deal with that and go to tension 2. I think our torque arm length is R for the radius. That's capital R here for if nothing else to differentiate the generic R. And I'll just go ahead, if you want, I can put something in there, say that's R. The size of the force is T1, and it's on a pulley, so sine of 90 degrees. The direction, on the other hand, let's see. Torque arm is up. The force is to the left. That is a torque that is out of the board. And that's negative for this case. I made into the board positive. That's clear in my diagram that into the board is positive. So this is a negative torque. So this torque is negative. The next torque arm R, force T2, sine 90 degrees. I think that's all pretty much the same. Right-hand rule again. My torque arm is this way. Force is downwards. That's a torque that's into the board. Into the board is negative. Into the board is positive, so put a positive sign there. Now again, writing out this little chart is nice. If you need to, you should do it. I don't know that I'm going to spend the space to do it all the time anymore. But I see 2 torques here. I'll reduce it down, and we'll get RT2 minus RT1 equals I alpha. I'm seeing a lot of writing. What eluded you before? So I want to start putting some stuff in here because I can't do it like this. I'm going to need to recognize that I have a disk and I know the moment of inertia of a disk. So that's one of those things that once you have your torque equations and your force equations, you need to start putting in information that you know. It's a disk, and that's 1/2 m, which is 2m. I'm doing this in terms of m, and the disk was 2m for that, right? 50 grams. R squared. And then alpha again. So if you want instructions there, do you know the moment of inertia? If so, put it into your problem. That's what that step was. At this point, I've got 3 relationships. These are the 3 relationships that are given to me by doing Newton's second law. If you'll remember from first semester, I made it pretty clear. Newton's second law doesn't tell you the answer, but Newton's second law will generate equations to which you might be able to determine something about your system. Now that we're adding torque, we're just adding another relationship in here. Anything that's spinning will have a torque relationship. These 3 relationships should be able to be used to determine the acceleration of the system. Now, I will point out that I don't have the same acceleration in all of these, and you should always take a moment to consider, in the system where the object is spinning, is this something that can be used to relate the linear acceleration of the objects that are moving in a translational way with the angular acceleration of the object that is spinning? Meaning, for one rotation of your object, do your translational objects move one circumference? If they do, you can use that. If they don't, you can't. There are situations where you will not be able to use that. In your homework, there are situations where you can't use that. You have a problem where, if you've started looking at your homework, and I know that's laughable, but let's say that maybe some of you have. There's a homework question that looks something like this, where you have a box on one side of a disk, but there's a inner portion that has a box on the other side. These 2 objects do not have the same linear acceleration. Right? One rotation of this wheel moves this box less than this box. You will have to be careful about how that works in this problem. On the other hand, both disks have the same angular velocity, acceleration, displacement. You need to be thoughtful. That's all I'm trying to say. We can use that in this problem, so I'm going to. And that will replace alpha with A over R. In this case, it'll be A over capital R. All right, that's it. What you do with this next is up to you. I said to find the acceleration, so I'm going to go about adding all of these together. Getting rid of all, I better say this. I'm noticing I can get rid of all the R's here again. That's going to happen a lot. Look for that when you can. But the R's will all cancel out here. So I will get T2 minus T1 equals 1/2 times 2m times A. I will also have mg minus T2 equals ma, and T1 equals 2ma. Pretty straightforward at this point. If I wanted the acceleration, I would probably just add all those together. I've got T2 and a negative T2, negative T1 and a T1. Those all go away, and I get mg equals 2m plus m times A. Right, 1/2 of 2m is just m. So it looks like A is 1/4 g. I think plugging your numbers in now is okay. Put in a 10, you get 2.5. But you could have done the whole thing in your grams and your G's and all that, and it would have been fine. Again, first time we're seeing it, but we're adding this to what is already stuff we've done. If you're struggling with the stuff over here and over here, be better. All right. Yes. No, I'm patient.
No, it's not a question.
All right. Again, this is a disk, mass M. We are holding this point and we are letting this unroll. I want to find the acceleration of the system. I'm asking you guys merely to come up with the forces on the system. Hopefully by now you realize you've only drawn 2 arrows because that's it. There's an upwards arrow for tension here. And there is a downwards arrow for weight here. And you should have drawn the weight arrow larger than the tension arrow because it accelerates downwards. These are the only forces acting in the system. So net force has to equal MA. So I have mg minus tension equals MA. That's it. We can't solve it with that, clearly, but that's the net force problem. So just because the system is rolling doesn't mean that there still isn't a net force problem. It's just that using net force isn't sufficient. Doesn't tell us what the tension is. I bet the tension depends on how difficult it is to turn this object. I bet if it's more difficult to turn this object, there will be a different value for tension than if it's easier to turn this object. I bet the tension goes up if it's more difficult to turn, because I think the acceleration will be less if it's difficult to turn. Are you understanding my meaning here? Without doing any calculation, if it's easy to turn, I bet the tension will be a small number because it's going to accelerate faster. This says right away that the acceleration is based on the difference between these two. The mass being the same, easy things to turn will have less inertia and will accelerate faster. That means the tension has to be less. Just doing the simple idea there, right? If it's impossible to turn it, well then T has to equal mg. But, I mean, impossible to turn. I mean, what do you attach a string to the earth and see if it falls? Yeah. All right, moving along. I think you're going to have to do a torque problem. Right? It's going to rotate, so I think you're going to have to do a torque problem. You have to make a decision, though. Because some of you see this problem one way, and some of you see this problem a different way. Do you want your pivot point to be here, or your pivot point to be here? Now, truthfully, it doesn't matter. In this problem, either will work to solve the problem, but only one of these is the actual pivot point. Pick one and do the problem. So you're either doing the problem at 1 or you're doing the problem at 2. I don't care. I'm not going to talk about why one of these is the right pivot point and one isn't. That'll have to wait till Monday because there's only 5 minutes left. But pick one. Yep. Now, there's only 4 minutes, so I want you to know before you guys leave, the answer is 2/3 G if you've done it right. But let's work it. I'm going to work both of these problems. You should be partway through. If we use 2 as our pivot point, then the tension is causing a torque, a positive torque, because it's causing it to rotate in the direction the system is moving. And I made downwards positive. So into the board is also positive. So the torque for pivot point 2 is going to equal I alpha, which is going to be RT equals 1/2 mr squared times A over R. Just going all the way with it. It's a disk, 1/2 mr squared. We would get alpha, but I'm pretty sure one rotation of the disk yields a change in position of 1 circumference. So I'm just cutting right to the chase there. And I get T equals 1/2 mr squared A. Now, if I do 1, the problem's a little different because the torque arm is now this distance. But it's not much different. The torque is still negative. The torque is still positive like I would expect. And I'll get R times mg equals, here's where I have to be careful. This would not be the moment of inertia of a disk. This would have to use the parallel axis theorem to figure out the moment of inertia. But that's not too hard. Parallel axis theorem would just be 1/2 mr squared plus, well, this is the shift distance, 1 radius. So I'm shifting it by mr squared. That's it, right? Parallel axis theorem. So RMG equals what appears to be 3/2 mr squared times A over R. Yep.
Why on the right?
Nope. I just forgot to cancel out the 2 R's over there. So, yep, made the change. We're good to go. Both of these yield the same answer. You may not see that, but they do. The left side, once I cancel out all the R's, I can solve directly for the answer without having to use the net force. Do you notice that? Right? This one relationship is enough for me to solve for A and find that A is 2/3 G. This side, I can't do that because I did it in terms of tension. I would have to use both of these to figure out the acceleration. But when I add those two relationships together, mind you, I get mg equals ma plus 1/2 ma. Which gives us, of course, mg equals 3/2 ma, so A equals 2/3 G. So you're going to get the same answer here, but which pivot point is the true pivot point? 1 or 2?
2.
It's 1. Now, if you want to know why, which part is actually moving instantaneously and which part is staying in place instantaneously? As a tire rolls, or anything rolls, the point in contact with the edge isn't moving relative to the rest of the world. That's where it's pivoting. For some of you, you think this is where the pivot point is, but it's not. That part is moving. The true pivot is here. That's not a big deal in this problem. It will be a big deal when we discuss rolling. All right.